In this video, we're going to go over entropy and the second law of thermodynamics. Now, a process is spontaneous because they are lowering their energy somehow. And when they lower energy, they release that energy into the surroundings. Now, most spontaneous processes, they will do this by releasing heat. So to go from a high potential energy to lower potential energy, they will release that heat. And we call that exothermic. However, there are some spontaneous processes that go from low potential energy to high potential energy. And for that to happen, they actually have to absorb heat, and so we call that endothermic. For example, let's look at this ice cube. This ice cube is melting. It's melting by absorbing heat. So this is endothermic. And therefore, the potential energy of the system's actually increasing. If we look at this gas here, we're going from liquid to gas. And so here, we're releasing energy when we do that, so the potential energy is decreasing. But we know both of these processes are spontaneous. And the reason why they're spontaneous, both of them, is because of what's called entropy. And the second law of thermodynamics states that any spontaneous process, the entropy of the universe has to increase. So here we will use the symbol S for entropy. And so any process that is spontaneous, the entropy of the universe must be greater than 0. The way you can think of entropy is chaos. If the chaos or disorder or randomness of the universe increases, then that process will happen spontaneously. The universe hates chaos. The universe loves disorder. Sorry, the universe hates order. It loves chaos. There we go. Now, if something is spontaneous, like I said, the entropy of the universe increases. Entropy itself is a state function. What that means is we don't care the path that entropy takes. To calculate the change in entropy in a system, all we need to know is the final entropy and the initial entropy. And so if a process is spontaneous, but the entropy change of that process is unfavorable, that is, something became more ordered. Well, if your system became more ordered, then your surroundings must have become more disordered, because your system is part of the universe. And for something to be spontaneous, the universe itself has to become more disordered. And so the surroundings have to be disordered. And for that to happen, your system will release heat into the surroundings. And when it does that, it makes the surroundings more disordered. So exothermic. So that's the way to think about it. If a process is exothermic, it releases heat to the surroundings to increase the chaos of the surroundings. So the surroundings become more disordered. If a process is endothermic, it is taking heat within to itself, and it's going to become more disordered, and that is how the disorder of the universe increases. Right? So when determining if something is spontaneous or not, you have to look at two things. You have to look at enthalpy or heat change and entropy or chaos change. All right? So we talked about enthalpy last semester being delta H, and that's when you look at the change in your internal energy and any PV work that was done. For delta S, that is the randomness of the reactants compared to the products. And to calculate randomness, to calculate this entropy, we need a formula, and that formula is given to us by Boltzmann. And Boltzmann's formula is entropy equals K ln W. K is what's known as the Boltzmann constant, and it's just a number. W is the number of ways, energetically equivalent ways, a system can exist. And this doesn't have units. So let's actually look at what W actually means in this case. And we're going to do that by looking at this chamber filled with 4 gas molecules. So this chamber, these 2 chambers rather, connected by a pipe. And right now, a valve is closed, so the gas has to stay in this part of the chamber. As soon as I open this valve, the gas molecules are free to be either in chamber 1 or chamber 2. They can move through the pipe, but you'll never find them in the pipe. You'll only find them in chamber 1 or chamber 2. So, let's say I open up the valve. What will happen? Well, intuitively, we know some of the gas will go over to the other side. But let's actually look at all the possibilities that could happen. So the first possibility is none of the gas moves. You have 4 molecules on one side, 0 molecules on the other side. Second possibility, 1 moves over. Then we have state C, 2 move over. State D, 3 move over. And state E, all 4 move over. And so if we look at this, we have 5 different states. And so the probability of being in each state, it should be 1 divided by 5, not 1 divided by 6. So therefore, every state has the same probability, right? So you'll find state A as the same frequency of B, C, D, and E. Well, we know that's not right because these are what are called macro states. That is just the big picture state. Each macro state can have microstates though. So state A only has 1 microstate. I can only put 4 gas molecules in 4 slots one way. State B though has 16 different microstates. If I have 3 gas molecules arranged like an L on the left side, I can put a gas molecule in the top left, top right, or bottom left. Okay, now let's do a different arrangement of 3 here. So top left, then on the right one, bottom left, top right, bottom right, and so on and so forth. And if we look at this, we find, well, there's 7 total possibilities. And state A, there's a 1 out of 17 chance of being in this possible state, so that's 5.9%. But 94.1% of the time, we're going to be in state B. Now, there is a way to calculate all these microstates without actually drawing them out. We're not going to do any of this in class, but here's the math for you, where it's the number of microstates equals B factorial divided by N multiplied by B factorial minus N factorial. B is the number of cells I can put stuff in, and N is the number of objects. So I can just calculate the possibilities of my left side times the possibilities of my right side. And I get that state A, there's 1.4% chance. State B is 23.9% chance. State C is 52.17% chance. And state D is 23.91%. And so if we're going from state A, which only has 1 possibility, so it has very low entropy, we're probably going to go to B, C, or D because that has higher levels of entropy, higher levels of chaos. And so doing that increases the disorder of the universe. And now you might be thinking to yourself, though, that state C should be the one that's correct. If we open up the valve, the 2 sides should have equal pressure and gas molecules, but here it's only 52.17%. Well, that's because this is really a very simplified estimation. So instead of 4 cells, imagine that you had, a couple hundred trillions. Even that's on the low side. And if once you start making these cells more and more possibilities, we're talking about moles and moles and moles of possibilities, state C will grow to 99.9999% probable. And it all has to do with how many ways can we put matter in, or how many ways can we rearrange matter. The more ways you can rearrange matter, the higher entropy value it is, the more disordered it will be, and the more likely you are to find your objects in that state. And that's it for entropy. I will see you in the next video.